Today we're talking about how we can take something as ordinary as plastic and turn it into the super materials of the future. And the secret? Well, it's not some new exotic ingredient. It's about learning to think like a microscopic architect and literally building invisible cities inside the stuff we use every single day.
Okay, so let's start with the basics. Polymers. You and I, we just call them plastics. And they are everywhere for a reason, right? They're the absolute workhorses of the material world. Cheap, light, super versatile. But, and this is a huge but, they come with some serious limitations. I mean, they're awful at conducting heat or electricity, and a lot of the time they just aren't strong enough for the really tough jobs.
You know, for decades, the solution was pretty straightforward. If you wanted to make a plastic better, you just mix in these tiny particles called fillers. It's kind of like baking, right? If you want chocolate chip cookies, you just stir in the chocolate chips. And for a long time, that was the go-to method. But this is where everything started to change. A new question began to pop up in labs, a question that is totally rewriting the rules of material science. What if we stopped just mixing? And what if we actually started building inside our materials?
And that question, well, it leads us right into our first big idea, the filler network blueprint. This is all about going from a random mess of particles to a perfectly ordered microscopic city.
So the answer is the filler network. But what is that really? Well, imagine instead of those filler particles just floating around randomly, you build them into a continuous, interconnected structure inside the polymer. Think of it like building a microscopic highway system for strength, or a tiny power grid for heat running all through the material. And look, we are not talking about a small improvement here. As a recent paper from 2024 puts it, creating what they call a pivotal nanofiller network leads to an abrupt enhancement in properties. It's not a gradual step up. It's a sudden, massive leap. It's a total game changer.
This whole idea brings up a fascinating concept, a tipping point. There's often this magic number, what scientists call the percolation threshold. Let's say it's around 5% filler. Below that number, the particles are like little disconnected islands. But the moment you cross that threshold, bam, they all connect. A network forms, and the material's properties just go through the roof.
So if building this network is the goal, how in the world do you actually do it? This is where we get to open up the microarchitect's toolkit and see how they build these invisible cities.
First up, we've got the hybrid mix. And this strategy is just brilliant. Instead of using just one kind of filler, you use a mix. You use larger, round particles to form the main structure. Think of those as your major highways. Then, you add in smaller, needle-shaped particles to bridge all the tiny gaps. Those are your local roads, creating a super dense, highly connected network. Okay, this next one might be the cleverest trick in the book, the ice template scaffold. Here's how it works. You take your fillers and you mix them in water. Then you freeze it. As the ice crystals grow, they literally push the fillers together into this perfectly organized 3D pattern. After that, you just sublimate the ice, turn it straight from a solid to a gas, and you're left with this perfect porous scaffold. All you do then is pour in your liquid polymer and cure it. You've just built a perfect microscopic structure using ice.
The next tool in the kit uses an invisible force to get the job done. You can think of it like a magnetic hand that tells the fillers exactly where to go.
So if you do nothing, you get a total mess. The fillers are all over the place, tangled, and really inefficient. But if you coat those fillers with magnetic nanoparticles and then turn on a magnetic field while the plastic is setting, they snap into these perfect direct chains. You've just created super highways for heat or electricity.
And finally, if physics can't quite get you there, you can always turn to chemistry. The last tool is basically a form of chemical glue that bonds the whole network together.
So what they do is they actually change the chemistry on the surface of the filler particles. This allows the fillers to form super strong covalent bonds directly with the plastic around them. So you're not just creating a network inside the polymer anymore, you're creating one single, seamless, integrated super material. It's incredibly strong and way more functional.
Okay, so we've got this amazing toolkit, but what can we actually do with it? What are the results of all this microscopic architecture? Well, this is where we get to see tomorrow's materials today.
You know, one of the biggest bottlenecks in modern electronics is just heat.
High-powered chips get really, really hot, and that limits how fast they can run. But by building these networks, you can create thermal superhighways inside plastics that are normally insulators, pulling heat away from things like computer chips and LEDs.
And the effect is huge. In one study, a material with one of these design networks was put on a high-powered LED, and it kept the chip a full 16 degrees Celsius cooler. I mean, that is a massive improvement. That means better performance and a much, much longer life for our electronics.
And what about energy? In batteries, these networks are creating what you can think of as ion fast lanes. They let batteries charge way faster. And maybe even more important, for the next generation of solid-state batteries, they can stop the growth of these dangerous things called lithium dendrites. They're like sharp little needles that cause short circuits and fires.
For example, one team built a solid-state battery electrolyte with a 3D filler network and achieved a lithium-ion transference number of 0.701. Now, you don't need to know the physics behind that number. All you need to know is that it represents a huge leap forward in efficiency and is a critical step toward getting us safer, more powerful batteries for everything.
And it doesn't even stop there. The same exact principles are now being used to create materials that can help heal the human body. This is where we see some incredible biomedical breakthroughs.
Take bone repair, for example. Scientists have designed these advanced hydrogels with a porous, interconnected network. It's perfectly safe and non-toxic, but here's the amazing part. The structure allows the body's own cells to move in and start growing, and the material itself actively encourages the body to deposit minerals and rebuild the bone. We're talking about true tissue regeneration, all made possible by this kind of microscopic architecture.
So all of these incredible breakthroughs, they really bring us right to the edge of the next design frontier. It begs the question, with all these tools, where do we build from here?
Here's the bottom line. The secret is out. The future of advanced materials isn't just about what you put in them. It's about how you build with those ingredients. We've basically graduated from being simple cooks, just mixing things in a bowl, to being microscopic city planners, designing from the ground up.
And this leaves us with one final and really exciting thought. We are just at the beginning of this revolution. Now that we are becoming true microscopic architects with the power to build materials from the nano level up, the only real question is, what impossibly smart materials will we design next?